Hi, my name is Shreyas, and today I will be talking about Lie Algebras. So the talk's going to be split into three parts. In the first part, I'm going to talk about Lie Algebras. In the second part, I'll be talking about a special Lie algebra, SL2F, and its modules. In the third part, I'll be talking about an important problem in Lie algebras called semisimple Lie algebras. We're trying to look at their structure. Okay, so without further ado, let's begin. What is a Lie algebra? Well, a Lie algebra L is defined to be a vector space over some field, and for purposes of this talk, the field is assumed to be algebraically closed and characteristic 0, so we might as well assume F is C. So it's a vector space over a field with this Lie bracket operator. Now this Lie bracket operator is going to be bilinear, so we're going to have bilinear, and it's going to satisfy two axioms, and they are brackets xx is 0, and this so-called Jacobi identity. And keep in mind that from the first axiom, we can actually derive that brackets xy is equal to brackets yx. Okay, so now we have that. And so this is a generic Lie algebra, and I kind of want to give you some examples so you can see what's going on. So examples. The first example we'll go over is the abelian Lie algebra. This is kind of a boring Lie algebra. The Lie bracket of any two elements is going to be 0. So all right, and so that is the abelian Lie algebra. Now let's get into a more interesting Lie algebra. We have linear Lie algebras. There's going to be two of them. The first is called GL and F. So this is going to be the n by n matrices over the field F. Similarly, we're going to have SL and F. So these are still n by n matrices, but here the trace is 0. Alright, and what is the Lie bracket we're going to use? Well, it's going to be brackets xy is xy minus yx. So the brackets is just the commutator. And we can see for abelian, this kind of makes sense. If we have abelian, then while using this notion, xy is going to be equal to yx. And in fact, linear Lie algebras are very important because there's a theorem by Ado that every finite dimensional Lie algebra is a subalgebra of GLV. And for this talk, all Lie algebras are assumed to be finite dimensional. So let's just clarify something with SL and F. Is this really a Lie algebra? Well, if we take two elements, x and y, and we compute the Lie brackets, brackets xy is xy minus yx. But since trace of xy is equal to trace of yx, then the brackets will have trace of 0, which is nice. And so now we're going to turn to the object of this talk called semisimple Lie algebras. So I'm not going to define them here, but there's multiple equivalent notions of semisimple Lie algebras. One is that there's a nice form called the killing form on Lie algebras, and it ends up being non-degenerate on semisimple Lie algebras. Another is that semisimple Lie algebras have no abelian ideals. But whatever, they have a very important role in what we're going to do. Okay, so this is part 1, Lie algebras. Okay, so now let's go to part 2. So part 2 is looking at a particular Lie algebra, SL2F, and its modules. So part 2, what is SL2F? Well, recall that it's going to be the 2x2 traceless matrices. So a general element from SL2F is going to be of this form: A, B, C, and C. So as you can see, the trace is going to be 0, and we can actually split this element into A 1 0 0 minus 1 plus B 0 1 0 0 and C 0 0 1 0. Can everyone see that? Yes. So we have that this general element breaks into these 3 pieces. So these 3 pieces form a basis. And they're such nice elements, we decide to give them names. We call the first one H, the diagonal element. We call the next one X, and we call the last one Y. Now there are importance relations among H, X, and Y, which help us understand the Lie bracket structure. We have brackets HX is 2X, brackets HY is 2Y, and brackets XY is H. What's going to be useful for our purposes is that brackets HH is 0H, which follows from the axioms, but will be something we will use. Okay, so before we jump right into modules, the important thing to note is that H is diagonal, and that's going to be very useful for our applications. Okay, so let's jump right into modules. Okay, so part 2 continued. What is a module? So an SL2F module is going to be a vector space that SL2F acts on by its 3 elements, basis elements, X, Y, and H. So we'll give a more rigorous definition. So we're going to have the action of SL2F on the vector space, and we're going to call that dot. So we have a dot, which goes from L times V to V. And it's going to satisfy a nice property, which is that if we have A, B, and L, and V and V, then we have this holds. Brackets AB dot B is equal to A dot B dot B minus B dot A dot B. And this kind of looks familiar because we're used to AB minus BA from our linear Lie algebras. And we know every finite dimensional Lie algebra sits inside a linear Lie algebra. Okay, but this is a little bit of a confusing picture. So I like to think of, we have one big vector space V, X acts on it, Y acts on it, and H acts on it. And in particular, since H is a diagonal element in SL2F, by some advanced theory, we know that H is actually a diagonalizable operation on V. So H and V to V is diagonalizable. And because H is diagonalizable, we are able to decompose V as a sum of eigenspaces according to the action by H. So V is going to be the direct sum of V lambda, where V lambdas are going to be the eigenspaces. We like to call them weight spaces, and the lambda is the according weight. Okay, but since V is finite dimensional, we know there's going to be finitely many V lambdas. Okay, so now we're kind of curious about the structure, and we know that we already have an example of an SL2F module. SL2F is itself an SL2F module. Now, why is that? So SL2F is going to have the 3 elements H, X, and Y. And we know H acts on H, X, and Y by, it's B minus 2Y. by doubling x, taking minus 2 of y, and killing h. So we have the three weight spaces, v minus 2, so call v SL2F as a vector space, v minus 2, v0, and v2. And we know that y is in v minus 2, h is in v0, and x is in v2. So this general pattern we'll see applies in a more broader context. But first, we will need the lemma that if we have v and v lambda, then x is actually going to move us up 2, and y is going to move us down 2. So x dot v is in v lambda plus 2, and y dot v is in v lambda minus 2. And the proofs of these we can kind of see by just applying h and using this fact. But okay, so this lemma helps us a lot, and it actually helps us classify what are called irreducible SL2F modules. So irreducible module basically means that there's no smaller modules besides 0, trivially. So we're looking at irreducible SL2F modules, and the key idea is we want to take an element, v and v lambda, where lambda is maximal. Now we're going to apply y a lot. As we know, y is going to take us to lower and lower weight spaces. So y dot v, y squared dot v, y cubed dot v, and so on. So y to the n is eventually going to kill v. Now we can write yn dot v. There's some work to show this, but we can write this as lambda minus n plus 1. And so lambda minus n plus 1 is 0. And lambda is n minus 1. This indicates a close relationship between the maximal eigenvalue and the dimension. So the eigenvalues are integers, at least for these elements, which is very surprising. And in fact, this is the surprising result, which I'll show you in just a moment. So, let's write our result. The result states that of dimension n plus 1, which is at least 2, we're going to have that there's going to be a unique irreducible module, which we call Vm. And Vm can be written as v minus m plus v minus m plus 2. And so we're going to keep adding 2's until we get this. So as you can see, there's a lot of properties I want to state. Each of these eigenspaces are of dimension 1. The eigenvalues are all integers, and they're all centered around 0. And finally, when we have different eigenspaces, x will carry us to bigger and bigger eigenspaces, while y will take us back, as we know from the lemma. So this is the irreducible module picture, and now we need modules in general. So now we're going to look at a general finite dimensional module. Okay, everything here is going to be finite dimensional. This irreducible module, the answer was for finite dimension. Okay, so for a general finite dimensional module, we have to take some vector space V. And because SL2F is semisimple, by Weyer's theorem, V will be decomposed as the sum of irreducible submodules. So Vi are going to be the submodules. Irreducible submodules. Somewhat irreducible submodules. And we can only accomplish this decomposition by Weyer's theorem. And what this is saying is if I know how each of these irreducible submodules look, I can just direct sum and then compute the picture for V. And I want to show a quick example for this. So let me erase this stuff over here. Let's see. So yeah, I'll work right here. Let's do a quick example. Let's say we have a general vector space and we're splitting into four irreducible modules. So, okay, our picture might look like this. Assume we're just working with these eigenvalues of -2, -1, 0, 1, and 2. Now, the first irreducible guy could just be something in V0. The second one could give us something in V-1 and V1. The third one could give us -2, 0, and 2. And the fourth one could just be V0 again. And then to get the entire picture for V, we just have to smash together all of these values. So we have V0 has dimension 3, and then everything else is dimension 1 for this general this general finite dimensional module. So this is the picture of SL2F and its modules, and now we'll move on to part 3. Now we are on part 3, looking at the structure of semisimple Lie algebras. Okay, so we're going to assume a lot of things which are needed, but just keep in mind that the structure, the representation theory will lend itself nicely to the structural theory. Okay, so part 3, let's say we have a semisimple Lie algebra. We'll call it L. Now, to every semisimple Lie algebra, there's going to be a maximal toral subalgebra inside. So a maximal toral subalgebra H sitting inside. What does toral mean? Toral means that all of the elements are diagonalizable. All of the elements are diagonalizable. And it's the fact that if we have a toral subalgebra of a semisimple thing, it's going to be abelian. Well, actually, any toral subalgebra is abelian. And that means everything commutes. All right, so we have H, which is a bunch of diagonalizable things that commute. We know from linear algebra that we can diagonalize all of them at the same time. So H acts on L with respect to some basis as a bunch of diagonal things. Therefore, we can decompose L into H plus a bunch of these L alphas, where alpha is going to be in the dual. So you can think of L alpha as the set of things for which H acts on the space. So H dot X. So it's a set of things where H acts on the space, as does alpha, which is some function from H to the ground field F. And it turns out that H is going to be everything that consists of L0. And so we have some kind of decomposition, and we'd like to explore this decomposition. So what is our picture? We're going to have H is something, and let's say it has a dimension of, let's say H has dimension of n. So it's going to be some big abelian thing. Now, we want to investigate what L alpha looks outside of H. So let's say we have L alpha over here, and we know that there's going to be some L minus alpha over there, simply by transferring the elements. Well, actually, it's not that obvious to show it, but I will gloss over that detail. So it can be shown that there is some X alpha in L alpha, some H alpha in H, and some Y alpha in L minus alpha, such that these three elements form a basis, are a copy of SL2F. These three elements, let me write that. That's very important, so let me write that down. All right, what does that mean? It means that we have our three multiplication properties, X alpha, Y alpha, H alpha, X alpha is 2X alpha, and H alpha, Y alpha is minus 2Y alpha. And this is going to be very important. Now, the question arises, are there more L C alpha, where C is not going to be plus or minus 1. The answer, surprisingly, is no. And this surprising fact will kind of be demonstrated. So let's see, I'm going to erase this first board. Apologies for all that noise. All right, let me redraw the picture so we have a sense for what's going on. We have our big H of dimension M. We have our L alpha out here. And we have our L minus alpha. All right, so the question is, are there more LC alphas? Now, what would that look like? Well, that would mean we have maybe some L2 alpha over here, some L alpha over 2 there, maybe some L minus 3 alpha over there, and our picture gets messy. But what can we do? We actually know this whole big picture, H with all the LC alphas, is going to be one big fat SL2F module. Why is that? Well, it's hard to give a concrete reason, but I'll give a more intuitive way of looking at it. It turns out that L alpha, LC alpha, is going to be LC plus 1 alpha, where C is not minus 1. And this means that the X alpha and Y alpha is going to transport us up root spaces and transport us down root spaces. And so, therefore, these three elements, Y alpha, H alpha, and X alpha, kind of act by going between root spaces. And that's why the whole thing is going to be an SL2F module. So since it's a big SL2F module, but finite dimensional, we can use our weight spaces theory from earlier. Okay, so because we're looking at a general module, we'd like to look at the irreducible pieces. So there's going to be a couple places where irreducible things pop up. First, we have H minus H alpha is going to be, or kernel of alpha, is going to be a space where X alpha, Y alpha, and H alpha are just going to kill everything in it. Therefore, we can this has dimension n minus 1, so we removed H alpha. And so therefore, this thing will split into n minus 1 irreducible things of weight 0, because everything's just going to kill it. All right, so what is our weight space picture? We have V minus 2, V minus 1, V0, V1, V2. And then weight spaces beyond 3 and minus 3 we still have, but we'll not write them for now for space reasons. Okay, so this is going to give us n minus 1 things in the weight space of 0, because X alpha, Y alpha, and H alpha are just going to kill everything in there. Okay, but we also have Y alpha, H alpha, and X alpha. I neglected to say that X alpha, Y alpha, H alpha is an irreducible SL2F module. And so that's going to give us another irreducible module. So that's going to give us a weight of V0, V2, and V minus 2. All right, so that's like the middle part of our picture here. Is there more stuff? The answer is no, and we'll see why. If there was another even weight, we would have to include the weight of 0 again by the whole symmetry thing. But we've exhausted all the weights of 0 because they would have to be inside H. Therefore, no more even weights. No more even weights. All right, that says that L2 alpha is not a root space, and yeah. And what does this say? It means that if we have a root, double of a root can't be a root, based on our reasoning. But what if we had odd ones? let's say we had some odd weights, like L minus 3 alpha is going to give us some odd weights. The problem is that because of the symmetry, we know we're going to have a weight of 1. But what does a weight of 1 mean? It means we have L alpha over 2. And if L alpha over 2 is a root space, L alpha can't be a root space. So L alpha over 2 can't be a root space. And so we have no odd weights either. This is the only thing there is. So our picture is just going to be H followed by a string like that. And as we add all the maybe not linearly independent, but as we add all the other root spaces, we're going to have H, which is a bunch of strings. Oh, and I forgot to say, L alpha and L minus alpha each have dimension 1 by this representation theory. And so our picture of semi-simple Lie algebras looks like this. Thank you.